Now that we have distinguished between the way that antenna radiation patterns are plotted, either using the radiation power density P or using the radiation intensity U, and P being a function of R, theta and phi, and U just being a function of theta and phi, now that we understand how these functions turn into radiation plots or radiation patterns for either the field or for the power, we can begin to look more formally towards defining antennas according to the radiation properties about these plots. And so what we're really interested in are specific characteristics of these plots. And the first that we're going to look at today is beamwidth, which we've already alluded to in some previous videos. But as stated earlier, an important figure of merit for characterizing your antenna is going to be the beamwidth, which tells us how spread out the antenna's main lobe is. The narrower the beamwidth of the antenna, the more focused the antenna is, and the wider the beamwidth, meaning the wider that the main lobe is, the less focused the antenna is. And all other factors held constant, a narrow beam will see over a smaller area but will be able to transmit further, whereas a wide beamwidth will see over a larger area but won't be able to transmit or receive over quite as large of a distance. Typically, when we use the term beamwidth, what we're talking about is called the HPBW, which is the half power beamwidth, and it's the angle on the radiation pattern between the two directions in which the radiation intensity is 1/2 of the value of the maximum radiation intensity. So here in this two-dimensional plot, this has been scaled to plot radiation intensity, so it's normalized here. And so the max value of the normalized function is 1. So the half power beamwidth is we go in both directions from the major lobe. We find out where that value is 0.5. If this is a power plot, that would be 0.707. If that was a field plot, it would be -3 dB if this plot was in decibels, because -3 dB is the 50% power location. So depending on what type of plot, you're either looking for 0.5 if you're looking at a linear power plot, you're looking for 0.707 if you're looking at a field plot, or -3 dB if you happen to be looking at a power plot in decibels. So anyway, the half power bandwidth is just the angular separation between these two points. So a second beamwidth, which is called the FNBW, or the first null beamwidth, is the angular separation between the first nulls in the antenna pattern plot. And as you know, a null is just an area of relatively low radiation, or we say zero radiation. And so the first nulls are the nulls on either side of the major lobe here. So the first null beamwidth is just this angular separation here. And so the value here and here of the radiation plot is 0. So in characterizing an antenna, we're usually concerned about the half power beamwidth. The reason we use first null beamwidth is that very often FNBW is used to approximate half power beamwidth by using the approximation that half power beamwidth is approximately equal to first null beamwidth div 2. We'll find situations where actually calculating half power beamwidth is difficult. It's much easier to calculate first null beamwidth, and so we use this formula to approximate the values. Okay, so over here I have two antenna plots. One's a 3-dimensional antenna plot and one's a 2-dimensional antenna plot, and these are actually plots of normalized radiation intensity, and that's U of 0, phi is equal to, in this case it's only a function of phi, it's independent of our position in, it's only a function of theta, it's independent as a function of phi, so we say it's just a function of theta, and it's cosine squared of theta, cosine squared of 3 theta, And this is for the condition that theta is less than or equal to 0, or is greater than or equal to 0 and is less than or equal to 90 degrees. And for all phi, that's a 0. Sorry, not a theta. So if I were wanting to find half power bandwidth, remember that this is in watts per steradian, so I can just go ahead and use this guy, and I can say U of theta is equal to 0.5. That's going to give me my half power bandwidth. Where does that occur for this function? And so we just set that equal to cosine squared of theta, cosine squared of 3 theta, and we have to solve this. So the first step would be to take the square root of both sides. So we get 0.707 equals cos theta cos 3 theta, and it's like, oh, wait a minute, how do I solve that? So you see, this is a situation where solving for half power bandwidth would be relatively difficult. The only way I know how to solve this problem is using numerical iteration techniques, which is a little advanced for this course. So instead, what we would do is we would solve for half power bandwidth by approximating it using this function right here. So let's instead set U of theta equal to 0, and that's going to be equal to cos theta cosine of 3 theta, where I've already taken the square root of both sides, right? Square root of 0 is just 0. So this we can kind of intuitively, we know, well, this will be true if either this function cosine of theta or this function cosine of 3 theta is 0. So we've got two solutions. Cosine of theta is equal to 0, and cosine of 3 theta is equal to 0. And this occurs at 90 degrees, and this occurs at 30 degrees. So the first null beam width is actually going to occur at the smaller of the two angles. Theta is equal to 30 degrees, but remember that's only going to be on one side of the radiation plot. So first null beam width is going to be equal to 2 times theta, which is equal to 60 degrees. So I can approximate half power bandwidth just by dividing first null bandwidth by 2. And so I get a value of 30 degrees for the half power bandwidth. If I had actually used some sort of iterative solver to solve for the half power bandwidth, I would have found out that the actual solution to this problem is 28.65 degrees. So it gives us a pretty close approximation if we use that half power bandwidth approximation formula. At this point, I'd like to point out that radiation patterns of most practical antenna are extremely complex, and presenting a closed form mathematical solution to describe this is usually pretty impossible to actually have. So even for many antenna where we can obtain a closed form expression, and by that just mean that we can represent the antenna pattern as a nice mathematical function, the equations are often so complicated that finding radiated power through integration is virtually impossible. And therefore, there are a lot of techniques to actually solve these problems. I just want you to know that those techniques are actually outside of the scope of what I can do in an Intro to Electromagnetics course. If you want to know more about solving these for Yagi antennas and more advanced antennas, you'd have to take an advanced course on electromagnetic theory as applied specifically to antennas. So I'm going to, in our work, just limit us to closed form mathematical expressions that describe these radiation patterns. Just know that life isn't that simple. Usually equations like this don't exist to describe the radiation pattern.